We're looking at exponential growth and decay in terms of compound interest, because compound interest is a form of exponential growth. We'll start with a really quick reminder. If you get this, you're quite welcome to skip it. When we're increasing or decreasing by a percentage, for example, if I'm increasing by 10%, then what I'm finding is 110% of the amount. If I'm decreasing by 10%, then what I'm finding is 90% of the amount. And you'll remember that if I'm finding a percentage of an amount, I do the percentage divided by 100 times the amount. So this would be 110 over 100 times the amount, and this would be 90 over 100 times the amount. And if I evaluate that, 110 divided by 100 is 1.1. 90 divided by 100 is 0.9. So if I multiply an amount by 1.1, I'm increasing it by 10%. Increase by 10%. If I multiply an amount by 0.9, I'm decreasing it by 10%. So this is just a reminder concept about multiplying by an amount greater than 1, increases by a percentage, and that's growth. If I'm multiplying by an amount between 0 and 1, and less than 1, I'll be decreasing by a percentage. So this is decay. So, a reminder that this little concept is important. And we can model this growth or decay with this rule. A equals Ka to the power T. You'll see this modelled or given with different letters at different times. And this is actually the compound interest formula in a simpler fashion. So we'll have a look at this. Our compound interest formula is the amount equals principal times 1 plus the interest rate over 100 to the power T or N. Now here is where we did the interest rate, the increase of 10%, plus, over 100 plus 1. So 10% over 100 is 0.1, plus 1, the original amount, means I'd be finding 110%. So you can see that this bit here is quite similar to what we just did there. K in this is our original or initial amount. So that equates to the principal in compound interest. A is our growth or decay factor. So this would be our growth factor in compound interest. And, mental blank. Let us work through this. A is the amount after time T. K is the initial amount. Oops. A is our growth or decay factor. T is our time. Now, if R is our rate of change, that is, say, 10% increase or a 10% decrease, then for growth, increasing, A equals 1 plus R on 100. Increasing by 10%, I'm adding 10%. For decay, for a number that's decreasing over time, A is 1 minus R on 100. So here, when I'm decreasing by 10%, that is 1 minus 10 on 100, which is 1 minus 0.1, which is 0.9, which is the other way of getting that. So you can see that for compound interest, which is growth, the amount is the initial value times the growth factor, which is 1 plus R on 100 to the power t. It is the same formula. This is just simplifying. Now, a little note about growth and decay. That growth, the amount is greater than 0, and decay, the amount is between 0, sorry, not the amount, the growth factor. The growth factor is between 0 and less than 1. So you might want to pause there and check that you've understood how we're using growth and decay to get A, our growth or decay factor. We could summarize our formula as the amount equals the amount with a subscript of 0 to say the amount at time 0 times 1 plus or minus the rate over 100 to the power n. So, both of these are our very important formulas. And this is, of course, our compound interest formula, which we've learnt before. They are the same formula. The amount equals the initial value times the growth or decay factor to the power of the number of time periods. So, to use this, let's have a look at the sort of questions we might want. For example, writing exponential rules. We have to define our variables and put them into a growth or a decay factor. So if John invests 100,000 in savings at 14% per annum, that's growth. If the city's population of 50,000 is decreasing by 12% per year, that's decay. You would define your variables. So for situation 1, let A equal the amount of money and let N equal the number of years invested. So our basic formula, you can represent it as the A equals Ka to the power of t, or, since they're both good formulas, we could have A equals A to the A base 0, 1 plus or minus R on 100 to the power n. Either of these are fine, so I'm doing them both. You don't need to do both. So, the information that we've got, the amount of money is what we want to be finding. I need the initial investment. So that's either K or A0. I'll work through it with this one, with this first question. So K equals 10,000. 100,000. And A, the growth or decay factor, is going to be 1 plus R on 100, because it's growth, which is 1 plus 14 on 100. Oops, running out of space. 1.14. That is A, our growth factor. And then into that rule, we would put what we've got. The amount equals K, 10,000, 100,000, I'm sorry, times the growth factor of 1.14 to the power of n number of years. We have written an exponential rule. We've defined our variables and used the exponential formula to write, this is the rule for the amount of money in John's investment after n years. We'll look at the second question, for which I will need more space. So for the second question, a city's initial population of 50,000 is decreasing by 12% per year. I'll use this one. You could use this one. That would be fine. Define our variables. Let P equal the population. It's per year. Let N equal number of years. Now here our initial amount is A0. So A0, it starts at 50,000. And then I've got to find 1 plus or minus R on 100. I've got to choose whether it's plus or minus. It's decreasing, so it's minus. So my rule, A equals A0 times 1 plus R, or plus or minus R on 100 to the power N. The amount, this is P for population now. The population is 50,000 times 1 minus 12 on 100 to the power N. And I'd simplify this. And 12 divided by 100 is 0.12. 1 minus 0.12 is 0.88. So this is 50,000 times, or in brackets, 0.88 to the power N. This is the rule for finding the population in this town after any particular number of years. I get the rule by taking the rule for exponential growth or decay and substituting in the value I know and simplifying. That's been a fair bit of time. That's like 13 minutes. If you want to stop and do the first few questions and then come back and watch this, that might be sensible. So the next question, house prices are rising at 9% per year. Zoe's house is currently valued at 145,000. So to start with, write a rule for the value of Zoe's house. It's increasing. Let's use A equals Ka to the power T. They've given the example actually. Let V equal value of house. N equals number of years. Now the initial price, K, is 145,000. And we have to find A, the growth factor, which is 1 plus R on 100, plus, because it's rising, 1 plus 9 on 100, that's 1.09. You can skip that working there. You should be able to go straight to here. So, we put this into the rule. V is the value of the house, which is 145,000 times the growth factor to the power N. That's the rule for finding the value of Zoe's house after any number of years. And that's helpful because now I've got to use that rule to find the value next year. So that's currently is year 0, so this will be year 1. Write the rule. Substitute in the value of 1 for 1 year. and evaluate that, which is $158,050. In 3 years' time, we'll start with the rule, and n will be 3. Oops. And we'll use the calculator for that. So in 3 years' time, it's worth 187,779.21 cents. Again, at this point, it's quite sensible to stop and come back to this type of question. I'm going to do this one a little bit cleverly. They've said, when will her house be worth $300,000? Now, the textbook says to do this with trial and error. I don't think that's very sensible. If it's trial and error, I mean, look, it's obviously not worth $300,000 after 3 years. You might try 6 years, and then try 7 years. And they've asked to 1 decimal place, so you're actually going to have to be sitting there going, try the power of 5, try a power of 6, try a power of 9, that's too much, try a power of 8. Trial and error you can do. I mean, look, we'll do one. 145,000, oops, 1,000 times 1.09 to the power 8. Hey, it's pretty close. But we haven't got to 300,000 yet. So we'd try 9, then we'd try 8.1 and 8.2. It would get really tedious. This is an exponential equation. When will her house be worth 300,000? Put down the rule. Value is 145,000 times 1.09 to the n. We want the value to be 300,000. 300,000 is 145,000 times 1.09 to the power n. Solve this equation by dividing both sides by 145,000. And this is an exponential equation. We're finding an unknown exponent. We learned how to do that. We use logs. So yes, you can use trial and error, but let's use logs instead. Let's divide this out, 300,000 divided by 145,000, 2.069. So let's rewrite. 1.09 to the power n equals 2.069. A nice simple exponential equation. Do you remember what we do with it? It's on page 632 of your textbook. If you're not sure, we take log 10 of both sides. Oops. Log 10 of both sides. N comes down to the front. Remember, this line really isn't that necessary. And this is n times log 10, 1.09, so we divide both sides by log 10, 1.09 to get n on its own. And then it's something you can enter into the calculator, because the calculator does log 10. So, log 2.069, divided by log 1.09, look, 8.4 years. Much easier than trial and error because we know how to use logs. Sorry that one was so long.